Hello and welcome back to PC Retro Programmer. In this video we're going to be extending the circle drawing routine that we started implementing in the previous video using the midpoint circle algorithm. You remember that it only drew an octant of the circle for us so far, or 1/8 of the circle. And our mission in this video is to extend that to a full quarter of the circle. Now we're going to do that by exploiting symmetry. And here is what we have so far. This is the single octant. It starts at the rightmost point of the circle and goes down and to the left. And we want to reflect this about the x-axis so that we get the octant that starts at that same rightmost point but goes up and to the left. And so that'll give us a total of 1/4 of the circle drawn. Now it's not as trivial to do this as the online write-ups might lead you to believe. They just say that each point you plot, you just reflect about 8 ways and voila, you have a full circle. Now of course that's true if you're using a plot point function, but remember we're not doing it that way. We're doing it the fast way, at least in CGA, by keeping track of an offset in video memory and a bit shift within that byte at that offset. So we keep track of a color byte and a mask byte that's shifted appropriately. So that's going to complicate our efforts to exploit symmetry. And the other thing that's going to make this difficult for us is the register limitation that we have. We're virtually out of registers as it is, so obviously, keeping track of all the other points that we have to plot is out of the question on the 8088 and 8086 CPU. So there is a trick for doing this, and I've gone ahead and implemented this, and this is circle2.asm. So let's load that up and take a look at what's actually changed since the previous video. Now before I get stuck in today, I should probably point out that the routine that we're going to look at doesn't just draw the reflection of the octant that we had last time, but it draws both at the same time. So there's a really neat and very efficient trick for this that we're going to use, but of course it requires an additional register. Now if we'd actually run out of registers at this point, what we would have to do is use memory addresses. So you just load the values into memory addresses, but of course this is much slower than working with registers. And all of the arithmetic operations, for example, don't work on a pair of memory addresses. You have to have at least one register. So it really slows everything down to do things with memory instead of registers. But fortunately we don't need to worry about that because at the end of the previous video we had a spare register in the main loop. Unlike the line drawing code where all the registers are in use, we didn't need an iteration counter in the circle drawing, and so the CX register was never used. So we actually have the spare register that we need. Now unfortunately the CX register is not the one that I want to use. The trick that I'm going to do today is pretty particular about which registers it can make use of, for reasons that I'll go into a little bit later. And so it turns out that I really want to use the BX register for that. But we were already using that last time for the mask and color bytes, and so they need to be shifted somewhere else. And of course it still has to be a register with a high and a low byte, and so one of the logical choices for that was the DX register. So we now have mask and color in DL and DH. But of course DX was being used for something else last time as well, so there's a little bit of a permutation of registers that's gone on here. I mean, DX is now in SI and the decision variable D is now in CX. Now I left the DY assignment alone. That's still going into BP because the lead-in code only sets DY to 0, and we can do that anytime. So we might as well make it the very last thing we do, and that way if we choose the BP register, we won't actually be modifying the BP register until the very last moment before the loop. And you remember BP is used to access the arguments of the function, so it makes sense to modify that as late as possible. Now, of course, our offset still has to go into DI, and we're still using AX for the accumulator. That makes perfect sense. So I've gone through and made all those changes in the code, so the right registers are now used. And the other thing that I've done is incorporate a trick that I described in the third line drawing video for speeding up the lead-in code. So we found this really cool trick where you can compute 4 times the offset instead of the offset, and you can do that way faster. And I won't go through all the details because I described it there in that third video on line drawing, the one where we're combining the verticalish and horizontalish cases. And so you can go and watch that there if you want to see how it works. But it just meant that there's a little bit of rearrangement of the code, pretty similar to what we did over there for that trick. And then once you've computed 4 times the offset, at the very end you just divide it by 4 again to get back to the value that it should be. So rest of the lead-in code here is the same, other than the fact that we've just changed all the registers about. And this is the first line where things become different. It's the first line before the main loop starts, using this additional BX register that we've now freed up. And you'll also see when we go through the main loop that it really isn't much bigger than it was before. This trick is really efficient. So let me get to describing how that works. Now I probably should mention that I've been calling the horizontal line through the center of the circle the x-axis of the circle. So I'm not talking about the x-axis of the screen or anything like that. I just mean the diameter of the circle passing through that midpoint and passing through the starting point of each of the 2 arcs that we're drawing. So the way this trick works is that we're going to use our spare register BX to store the difference in bytes, the difference in offset within video memory of the current point that we're drawing and its reflection about the x-axis. So we'll just keep that information always up to date, each iteration of the loop. Now the reason this works out really well is because suppose you have a point on the circle that you're currently drawing and it's n scan lines below the x-axis. Well, its reflection has to be n scan lines above the x-axis. And so there's always a difference of 2n, so it's always an even difference in scan lines between the 2 points. Now that's important because that means if the point that we're currently drawing is on an even scan line, its reflection is also going to be on an even scan line. And if a point is on an odd scan line, its reflection is also going to be on an odd scan line. So a point and its reflection are always going to be in the same bank of CGA memory. Remember that in CGA memory we have all of the even lines first, so we call that the even bank, and we have all of the odd lines following, and we call that the odd bank. So a point and its reflection are always in the same bank. Now the other thing to notice is that if you have a 2n scan line difference on the screen, that translates to an n scan line difference within the bank that they're in. And that's because the banks only contain half of the scan lines. They've either got all the odd scan lines or all the even scan lines. And so 2n scan line difference on the screen corresponds to n scan lines difference in the banks. And of course a scan line is just 80 bytes, so the difference in offset is just 80 times n, where n is the number of scan lines the point is below the x-axis. So we just keep that value, 80 times n bytes, in the BX register, and we just keep it up to date every iteration of the loop. And that means that we can always get from the offset of the current point we're drawing to the offset of its reflection just by adding the BX register. So nothing could really be simpler. So what does this mean in practice? How do we keep the BX register up to date? Well, if we move by 1 scan line down in our circle drawing routine, so in other words we increment the y coordinate in our circle drawing, then all we have to do is just add 80 to the BX register. So nothing could really be simpler. So let's take a look at how this all works out in practice in the main loop. Now we obviously want to start with an offset difference of 0 before the loop starts, because the two octants that we're drawing start on the same pixel, the rightmost pixel of the circle, and they move out from there. So in other words, the first point and its reflection coincide, and so that's why the offset difference is initially set to 0. So let's scroll down to where the offset difference gets updated in the loop, and this should be where the y coordinate gets increased. So here's the original code that we had for incrementing the y coordinate. That hasn't changed, and this is the additional line that we've added. Now I'm actually not adding 80 here, I'm subtracting 80, and the reason for this is because when I'm moving from the original pixel to its reflection, the reflection is above the original pixel on the screen. So in other words, it has a lower y coordinate. And so that's why the y offset needs to decrease. And in fact, this bx will end up being a negative value throughout this loop. So the only other change that we needed to make to the circle loop here is drawing the reflected pixel. So here are the 4 lines for drawing the reflected pixel and the 4 for drawing the original pixel. Now these 4 haven't changed. That's identical to what we had before. And the reason that it's done second instead of first is because of the STOSB instruction. Remember that increments di when it's done, and so we don't really want to mess up the value of di before we run the reflected pixel code, so that's why it has to come second. But otherwise, the reflected pixel code is pretty much the same idea. You read a byte out of CGA memory, you do the AND and OR combination for the mask and color, and then you write back to CGA memory. The main difference is that the offset now has to be di plus bx, so where bx is this negative value I was talking about. So you really can't use STOSB here because STOSB only works with di, it doesn't work with di plus bx. So we really have to do the move manually, so to speak. Now you always want to use STOSB whenever you can because it's only a single byte of machine code, so you get a lot of power for very little machine code cost. This is a little bit slower to read into the CPU. There's actually 3 bytes here. This di plus bx here explains why we needed to use the bx register. I said earlier in the video that I'd explain this. So it turns out that the 8086 and 8088 only have a limited number of addressing modes. And that means that there are only certain combinations of registers that you can put in the offset brackets here. So whenever you use bx plus something or bp plus something, this is called base relative addressing. This is kind of ideal for us here because we can use it with either SI or DI, and in our case we need to use it with DI because of the STOSB. So we had 2 options. We could have done DI plus BP here, or we could have done DI plus BX. Neither of them are actually ideal. So whenever you use BP as the base register in base relative addressing, it's always with respect to the stack segment. And whenever you use BX as the base register, it's always with respect to the data segment, DS. And in our case, we actually want to use ES. So we have to put an additional bit of code here, this ES colon, to tell it to not use the default segment. So the default segment here would have been DS because of that BX. And so we want to use ES where our CGA segment is. So this is called a segment override, and it actually does cost you something. It's an extra byte of machine code, and so that's going to increase the cost to load this instruction in. Now there is actually a way that we could have got rid of this extra byte for the segment override. obviously we could set the DS register to have the same thing in it as the ES register, just copy the value over before the loop starts, and then we'd be able to get rid of all these segment overrides. We get rid of one here, and actually also one here, just by having the same value in DS, and then the default value of DS for the segment would have been fine in all three cases. So that's something we might look at doing in a later video, because that is actually a saving here, but I just wanted to keep it clear for now what's actually going on, so I didn't use this optimization. But at any rate, that's basically all there is to this code, and so the only other thing to do now really is to run this code and see how it performs. Before I do that though, I just want to talk about one point of programming philosophy here. Obviously we used a really cool trick here, this so-called base relative addressing for our reflection. And these extra addressing modes that the 8086 and 8088 CPU offer us are one of the strengths of those CPUs. So there are a number of things that these CPUs can do that, for example, 8-bit CPUs weren't very good at. So for example, the string instructions are also very, very powerful, especially when used with the rep prefix, which causes them to repeat. And there are a lot of side effects from instructions, the way the flags are updated, that you can take advantage of in a lot of cases. And of course it's a 16-bit CPU. You have 16-bit registers, and they can do 16-bit arithmetic operations, and there's also multiplication and division in there as well. So these are very powerful CPUs in a lot of ways. Very many things that take a lot of instructions on an 8-bit CPU can be done in a few instructions on this CPU. The other thing, of course, is they can typically address much more memory, and they're not limited to just 64K. You can move 64K segments about pretty much arbitrarily in memory, and there are lots and lots of tricks you can do using these segment registers, which is another very powerful feature of these CPUs. So keep in mind all of these additional things that it's offering you, and play to the strengths of the CPU. Come up with the facts and tricks and ideas that use all of the sort of nooks and crannies that the CPU offers in its instruction space, so to speak, to really get the most out of the CPU, and then you can actually demonstrate some really impressive code running on these things. So anyway, let's start by actually saving this, and then we'll assemble it and look at how it actually runs. So I've not changed the main driver here because we want to compare with how it was in the previous video, and so we'll just link this and run circle2, and voila, there we have a perfectly reflected octant. So now an entire quarter of the circle is drawn. Now, to my way of looking at this, it seems like this might be a very large circle, or maybe it's not. So this is a final thought I'll leave you with. Is this a large circle, or is it just an out of proportion circle? Are we even on the right track here, or is something going wrong? So that's something I'll come back to in a later video, and something for you to ponder in the meantime.